Hello, everybody. In this video, we're gonna continue where we left off last week. Hope everybody had a good weekend. Let me dive into here. So we're going to go over, let me share my screen real quick. We're going to continue where we left off with Riemann sums. So looking at this, remember what we talked about? So we were talking about a different way to find or to basically solve an integral, essentially, right? So previously, earlier last week, we talked about the most complicated ways to solve it right here, where we actually go through and solve it with what's called the limit definition of the integral, actually using the limit of a pretty complex summation. Remember, at the end of the day, that's really just rectangles under the curve, or the area under the curve we're approximating with rectangles, and we let the number of rectangles increase to infinity in the limit. So we talked about that, and then last time we talked about a replacement for that, where we where we find the exact area under the curve. And just like we did before, again, where you could solve this crazy limit like we did, but what we talked about is as you can see, a much more efficient way. So only a handful of steps. That's what we talked about. Now here, what we're going to do is we're going to dive a little bit deeper into this, because if you think about it, just as a refresher, this method is obviously significantly easier than the previous method of taking the limit as n goes to infinity of the summation, etc. This is significantly easier, except for one detail. There's really, I would say, one hard part about this, and that is this step right here, where we take the actual function we want to find the area under the curve for, and basically or I guess how should I word this? We have the function that we're trying to find the area under the curve for, and then we take the antiderivative of that. So basically, then we talked about that last time, right? The antiderivative is the function such that if you took the derivative of this, it would equal that, right? Derivative of 5x is 5. Derivative of negative 1/3 x cubed is negative x squared. So if we take the derivative of this thing, we get what we started with. But what we need to learn now is the ability, and we talked about this last time with the kind of the integral rules or the antiderivative rules, depending on how you want to word it, the ability to like start off with a function and take the antiderivative just as easily and just as smoothly as you can take the derivative. And after that, it's pretty easy actually. It's like we said, you just plug in the upper bound, plug in the lower bound, subtract, and you get your answer. You get the number that represents the true area under the curve. So that's kind of the idea. And then now, what we're going to do is we're going to kind of dive into how to actually do these. And before we do that, I'm actually going to introduce something for today. What this is called, just to introduce a little bit of terminology, this is called a definite integral. This is called a definite integral, as opposed to what we'll talk about in a second, an indefinite integral. So just for clarity, what do we mean by definite integral? A definite integral is, and actually let me create a little bit of a table here. So a definite integral is essentially where we know the bounds, right? So it's an integral as opposed, like I said, we'll talk about an indefinite integral here in a second. So it's an integral where we know the bounds as opposed to an indefinite integral, which I'll cover in a second. So a definite integral, we know the bounds, and basically the output is an area under the curve, right? Area under the curve. What we're going to start talking about is an indefinite integral, where, for example, it does not have any bounds. So if I bring this down, imagine if we did not know the bound, or if we did not know the bounds. So if we had this, so imagine that we do not know the bounds. This is an indefinite integral, and the output is a function. Now, why are we going to this trouble? So basically, here's what I'll say. It's the function that's the antiderivative. So just for clarity, the antiderivative is the function. So why are we talking about this now? So basically, definite integrals, what we have here, are the only things that are actually useful in like the real world, in solving physics problems, whatever. the area under the curve will usually mean something depending on, it really depends on the context of the problem, but it might be, let's see, what could it be? It could be like the displacement, the change in distance. It could be the change in velocity. It could be the change in energy. Like depending on what function you're integrating, it could mean many different things in physics. But the area under the curve is always some number, and it represents some quantity in physics. So that's kind of the idea for that. That's for the definite integral. Now, for the indefinite integral, the output there is a function. That by itself is not really useful. Remember, it doesn't really mean anything physically until we find the area. Like, right, it's really just the function that if we plugged in the two numbers, we would find the area under the curve. So why do we do this? Why do we care about the indefinite integral if it's actually, we can't use it for anything? Basically, we're doing it to practice definite integrals, right? So like in the last problem, we know that if we solve this definite integral, we get the area under the curve, which was 12, and we confirmed that that was right compared to what we did prior. So we confirmed that. Now, I guess, how should I word this? What we should do, or what we could do here, is we can talk about, right? We talked about the process. So this first step is to find the antiderivative, or the indefinite integral. This thing is basically the indefinite integral with one tiny adjustment. That's the function. But here, after you have that, the next step is obviously to plug in 2 and plug in -1. So basically, the understanding is, okay, yeah, in order to get anything useful out, like an area under the curve, you would need to know the bounds. In other words, you would need to have a definite integral. But it's assumed that if you're able to do that, this is the hard part. Like the first part is the hard part. Once you're able to do that, then you should plug in like the upper bound and the lower bound to there, so that you can see, so that from there, after you plug those in, then you can simplify it down to just get a final number at the end. So hopefully that makes sense. So even though the definite integral is the most useful thing, it's assumed that you basically know how to handle this part. Like if we can just do this first step, just find the indefinite integral basically, or the antiderivative, that's the hard part. That's the calculus part. And then after that, you can easily plug in whatever the bounds are to find the answer, which is actually useful for your question. So hopefully that makes sense. So even though this is not useful by itself, it's the hardest part of the definite integral, which is why we want to spend so much time on it, right? Because we don't really need to practice plugging in values into functions and subtracting. That's algebra, right? So it's assumed that you're able to do that, no problem. What we really need to practice is the calculus part. So that's what we're going to talk about. And we already talked about this. But here, what we're going to do is we're going to kind of just dive into some examples. So that's all I want to do today. This will not be comprehensive to learn all the ins and outs of the, I guess, how should I say it? This will not be comprehensive to learn all the ins and outs of the, of like these indefinite integrals. But what we can do is we can at least learn some generalities and kind of get a feel for the rules, right? So here, let me start off with this. Let's start off with this. So let's just say let's try to find the antiderivative of 0, which seems weird, but 0 is the simplest function I could think of. So what, and this for each one of these, by the way, like if you're watching this on the replay, feel free to pause the video. I recommend doing that and kind of guessing what you think the antiderivative is, right? So let's think about it. What function? Another way to remember, as we're finding these, we're trying to find the antiderivative of each of these. But for each of them in particular, what we really need to do is come up with the function such that if we took the derivative of it, it would equal what we're looking at here. So like what function, if we took the derivative of that, would equal 0? That's the question. So here, if you pause the video and think about it for a bit, hopefully it's clear that like 1 would work, right? 1 works, but also 2 works, 3 works, a million works, negative a million works. Literally any constant number works here if you think about it. If you take the derivative of a constant, it will equal 0. That means the antiderivative of 0 is just some constant. And you can just call that constant like c. So there you go. Hopefully that makes sense. So this function, and again, this is not really useful, obviously, but like we're just trying to get a feel for the rules. So hopefully that makes sense. The next one here would be like, what if I had, let's just bump it up a little in complexity. What if we're looking at x? Actually, let's actually do another constant. What if we said like 2? Or let's say 1 or 2. What would the integral of 1 equal? So here, if you think about it, hopefully this makes sense. And if you pause the video and think through some options, basically, hopefully it's clear that it would be x, right? So like and think about it, the derivative of x is 1. However, and this is where we're really just doing the derivative rules in reverse. That's another way you guys can think about this. That's what we're doing here. That antiderivatives or integrals, however you want to call them, are literally the opposite of derivatives. So we're doing them in reverse. Now here for this, there's actually another detail though, because like this is not the only answer. X is not the only answer to this antiderivative. Think about it. X plus 1 would work. X plus 2 would work, right? Because like we said before, derivative of a constant is 0. And if you do like the constant multiple rule, or sorry, not the constant multiple rule, the sum rule. So, and then if you have, anything, basically x minus 1,000, that would also work, the derivative of that. So those would all work. I guess my question is, yeah, so I'll just say that's kind of my thought process. And then what else could we do here? Well, how could we represent that the same way we did above, right? Instead of x plus 1, x plus 2, x plus a million, or x minus a million, whatever, it could be any number. And by the way we're like, if you think of the answer as just x, you're really saying x plus 0. So it's always x plus some constant here, which is, c in this case. So this is actually, if you think about it, the general solution. And just to spell this out, I think you hopefully get it, but just to spell it out a little bit more clearly, if you have the derivative of x plus or x minus, let's say x minus 100, and then we'll say the derivative of just x, and then the derivative of x plus 100. The derivative of all of these is 1, right? So if we're going to say what's the antiderivative of 1, these are all equally valid answers. And like I said, you can look at this as really x plus 0. So the thing that they all have in common is it's x plus something, or x minus is really x plus a negative number, but they all have in common x plus, and then you can plug in literally any constant you want there. Hopefully that's clear for why we need that when we're doing the indefinite integrals. We'll talk about this in probably maybe next, tomorrow on our live, or maybe the one after that. This doesn't matter for the definite integral, which is why it didn't pop up when we did that. We'll talk about why, but for the indefinite integral, I would like to get rid of the plus c, to be honest. If I was in charge of the curriculum, it's like I'll say it's a little inconsistent how they've applied it. I'll just say that much. But as it stands right now, in a typical AP Calc class, you'll lose credit on it. You'll lose credit if you don't add that. So we are going to need this plus c. And by the way, this is going to be for everything, right? Because like if we go up to the next one, so here let's now talk about, and hopefully, by the way, it's clear that I should say this before I go on. If we had like 2x, if we had the antiderivative or the integral of 2, it would just be 2x plus c, right? And like you could have any constant here, and actually I'll write that down like just to generalize that. So like I'll say 2x plus c, and then you have like the integral of 3 dx. You have 3x plus c. So those are just a couple of options. And again, we're just starting with the very basics here. We're just trying to understand how powers work, basically, when we're taking the antiderivative or the integral of those. So we'll go over that. And then here, let's bump it up now. Let's talk about the antiderivative of x. So the antiderivative of x, think about this. And we kind of talked about it above, arguably, if you know how to think about it. But what would the antiderivative of this be? So we talked about a technique you could use to figure this out. So what function, if we took the derivative of it, would equal x? That's the question. So here, when you take the derivative and you get x out, think about what power you would have had before doing that. Hopefully it's clear. X squared, right? Because like the derivative of x squared is 2x, right? So the derivative, like with the normal power rule that we're used to, every time you take the derivative, you basically bring a power out front and then you subtract 1 from the power. So, so like for example, if you take the derivative of x cubed, it will be 3x squared. If you take the derivative of 2 or x squared, it will be 2x. If you take the derivative of x, like we said before, it'll be 1. So the function that produces an answer of x would have to be something to the x squared. But if you think about it, like I just said, x squared, the derivative of that is actually 2x. We want just 1x here. So hopefully it's clear. We need to just divide by 2. So you can say x squared over 2, 1/2 x squared, however you want to say that. Those are both right. And then remember, logically, we always need this plus c for the reasons that we talked about above. So hopefully that makes sense. And then you can do other options here as well. So like if you think about it, what would be the antiderivative of 2x? Well, we just kind of said that, well, the derivative of x squared is 2x, therefore the antiderivative of 2x is x squared, and then plus c. So at this point, and we could keep going, by the way. So I won't go too long today because I know people are just kind of getting back into the swing of things for the beginning of the week. But actually, well, yeah, actually, I take that back. Let's do one more just to see this because we'll just reason our way through one more, and then we'll try to put together some patterns that we're seeing. Let's say so. Here we talked about that. What if we had kind of the next jump up? What if we had x squared? Well, if we have the antiderivative of x squared, think about it like this. We were kind of just saying that before. The derivative, like what function or what power would you have to take the derivative of to equal x squared? Well, according to the power rule, every time we take the derivative, we basically bring down a constant and we subtract one from the power. So what power would we have to subtract one to for it to land on x squared? That's kind of the question. So for that to happen, hopefully it's clear, it would be x cubed. So x cubed, right? And then again, the derivative of x cubed we already know is 3x squared, not 1x squared. So we want 1/3 of that. So hopefully it's clear, 1/3 x cubed. And remember, we always need the plus c with indefinite integrals when there are no bounds. If there are bounds, we don't need the c, which seems a little inconsistent. I agree. I kind of don't like that. That's why I was saying before I would change how the plus c would work in the curriculum if I was in charge, but I'm not in charge, so we're stuck with it. So I'll explain the difference later on, but right now you don't have to worry about it too much. You'll get in the habit of adding it as you do a lot of these. So that's that one, and then we can test some other ones too. So if I had like, let's say not 1x squared but 2x squared, what would that be? Well, think it through. So we already know that the derivative of 1/3 x cubed gives us 2x, or sorry, x squared. I mean, not 2x. If we want 2 times that, does it make sense? We kind of double that. So right, so we get 2/3 x cubed plus c, and you can test this out. This is the other thing, by the way. Like whenever you're doing an antiderivative, or you're finding an antiderivative, or you're finding an integral, it's a good idea to basically take the derivative of what you got and see if it's correct, right? So if you take the derivative of this side right here, right, take the derivative of that, it's 1. If you take the derivative of this, it's 3. So like that's how you can always check it. Whenever you're unsure if your answer is right, you can just take the derivative of it and see if that is what you started with, what you started off trying to integrate, right? Because like again, this thing is the antiderivative of that thing. Therefore, this thing has to be the derivative of that thing if you found the right antiderivative, that is. That's why you can check it that way. So here, if you do that, think about it. What would happen if you take the derivative of 2/3 x cubed plus c? Well, what would happen? We would bring the 3 out front, subtract 1, so it would become 2 right there. So the 3/3 cancel, or the 3/3 cancels out, and we go left with 2x squared, which is what we have here. So that's how you can hopefully see that that is correct. And we could keep going like this, by the way. We could talk about what the antiderivative of x cubed is, and 2x cubed, and 3x cubed. We could do this, for the rest of the day and still not be done. But ideally, what we'd like to do, because remember, I'll say this, I think I mentioned this last time, there are integral rules, right? There are integral rules. There are rules, just like there are derivative rules. You don't have to remember the derivative of every single function. You just have to remember the derivative of like 20, basically different rules. And if you know those 20 or 22 rules, depending on how you count, you can basically do everything you would want. Same story here, right? So if we know like 20 or so integral rules, we can do whatever we want. So here, what I want to do is I want to kind of just start seeing if we can notice any patterns here, right? So let's start seeing if we can notice any patterns here. So looking at the first thing here, so if we have the integral of, or actually, let's see. So yeah, let's talk about this. So first off, if you look at this first thing, so obviously we know that like when you're taking the integral of a constant, it's going to be a linear equation, right? We know that. Another way of saying that is the derivative of a linear equation is a constant. Same thing. But see if you can notice anything in particular between these. Like, what is going on here? If you notice, we seem to have, because you can think of this as a 1 here, even though we didn't write it. If you change the integral of 1, it's 1x. Integral of 2, 2x. Integral of 3, 3x. Hopefully it's clear that if you just remember this first thing here, like, right, if you just take this first thing, then, and you just remember that as a rule, let's say. Again, we can actually do a little bit better than this, but let's say this is the rule that you're rote memorizing. Then what you can do is if you like multiply by 3, let's say. So basically, if you multiply, actually, I'll just say this. If we multiply by 3 on the inside, so 3 times 1, and then do 3 times this whole thing, does it make sense? We get what we already established has to be true, right? The integral of 3 is equal to 3x plus, and you could think of it like this. You could think of it as 3 times c. But this is actually a little bit weird because when you're dealing with c is what's called an arbitrary constant in calculus with integrals. Basically, it's a number we don't know. So we know it's a constant, and again, it could be 0 even, right? So it could be 0, 1, -1, anything in between. It could literally be anything. We have no idea what it is. So think about it like this. Think about this question. It might seem like a weird question, but what is a number that we don't know times 3? Well, it's just another number we don't know. So why don't we just call the whole thing c if we're using c to represent a number we don't know? And yeah, it's going to be a different than the original c. That's true, but we didn't know what that was either. So who cares? You know what I mean? It's like if we don't know what the original one was, like we're not going to know what the final one is. So it's like it's just another unknown number at the end of the day. That's kind of how we can think about it. That's why when you do the math here, it doesn't seem like you're doing anything with the c. Like whenever you add or multiply or subtract or divide whatever with c, like nothing happens. It just stays c, and you'll see this pattern a lot over and over again as you work with more and more integrals. But hopefully that idea makes sense. And then now, what I want to focus on here is actually kind of a more important issue because if you notice this, think about it. If you remember, so remember what we just said here just a second ago. So if you're remembering this first rule here, so if you're remembering this first rule, so if you're remembering this first rule, then basically what we just learned is that okay, if you already believe this first rule is true, you can multiply both sides, like inside and outside the integral, by any number. So in other words, like another way you can think about it, what we're really getting at is something called the constant multiple rule, right? So this is like one of the simplest rules. And by the way, that might ring a bell. That should ring a bell, right? Because we talked about that with derivatives. So if you have 3 times, like if you're trying to find the integral of 3 dx, what you can do is you can factor out a 3. So if you factor, like look at this as 3 times 1, basically. So pull a 3 to the outside, and you're left with 1 dx, and you can solve that, right? So you get 3 integral 1. We already know that's x plus c, and we talked about before why just multiplying c by 3 is really just a different c. So you see how it gets the right answer, right? So that this is an important rule, and this works with everything, by the way, everything we did here, right? So if you know that the integral of x is 1/2 x squared plus c, well, if you're trying to find the integral of 2x, so if we bring this down here, let's use this same property. What we're saying is you can factor out, so you can factor out a 2. So you can factor out a 2, and then you have the integral of x with respect to x. We have the 2 outside here, and then the x is 1/2 x squared plus c, right? And then if you multiply through here, so 2 times 1/2 would be 1, so x squared plus 2c, or just c, which is what we already knew is right? This applies to anything. So it's like, of all the rules that we wrote down here, you really don't need that many of them, honestly. You don't need these, right? You don't need this. You don't need this. It's like if you just remember what the integral of 1 is, what the integral of x is, what the integral of x squared is, you can find the integral of like 100x squared just as easily, right? You just factor out 100, solve the x squared the normal way, and then multiply the 100 back at the end. that's actually, it seems simple, but that's a very powerful rule. It didn't have to work out that way, by the way. What we just discovered is called the constant multiple for integrals. And that should ring a bell, by the way, because there's also a constant multiple rule for derivatives. In fact, that's why this thing is true. Remember, every rule that we learn here has an analog, I'll say, for derivatives. We're literally doing the opposite of derivatives. So, like all the rules you already know, there's an opposite to them. So here, if you think about it, what is this really saying? If we have some constant times any function, and we're trying to integrate that, then that would be c times the integral of f of x dx. So hopefully that makes sense. And why is that true? Again, it's because there's another one. There's basically it's a very similar rule for derivatives, right? If you do c times f of x and you take the derivative of that whole thing, what is that? Well, that's c times f prime, the derivative of x. So just like you can with derivatives, you can pull out a constant, take the derivative, multiply by the constant. You can do that here with integrals too. So hopefully that makes sense. So this is just the tip of the iceberg, by the way. So what I'll do before we hop off for today, I'm actually going to leave you with something interesting. So there's again, this is like I said, just the tip of the iceberg. There are many more patterns like this. So if we're doing this, so here, or actually, sorry, that was not what I wanted. I grabbed the wrong one for that. So I wanted to grab the X. There you go. So for this one, there you go. So looking at these, see if you notice a pattern here, and we'll talk about it tomorrow. But see if you have a guess here, and I'll give you a hint. Think about like how each of these numbers work. So like if you imagine there's a one here, right? If x is really x to the one. See if you can like first off predict what the integral of x cubed would be, and like figure that out if you want. Because again, we don't need to worry about the constants based on what we just said. See if you can figure this out for tomorrow. Also feel free to like as you guys are figuring it out, feel free to like drop any comments in the Skool community, right? So like if you come up with the post, well, I'm hesitant to give it away, but it's not that big a deal. So yeah, if you discover this, feel free to like just comment under this video in the Skool community that you kind of know what it is, and then we can kind of go from there. But we'll do that to start, and then I'll just give a hint. Like there is a pattern here. There's actually a relatively simple rule that we can systematize from this. And after we know that, we'll know how to take the derivative of x to the 100th power just as easily as we can take the derivative of x squared. So give that a shot. If you come up with the answer, feel free to just drop a comment under this post. I'll upload this post in the Skool community afterwards for this recording. But yeah, otherwise, any questions on that from anybody before we go? Feel free to just drop them in the chat. But yeah, otherwise, if that all makes sense, feel free to, like I said, continue dropping questions in the Skool community. Right, you can post anything anytime. But other than that, I will see you all tomorrow, and we'll meet back again for our normal live. See you later.